Alright, time for another draftphysics.com video presentation. Alright, the air track experiments. Okay, so we'll just call this the first of the air track experiments. And so I just did it as crudely as possible just to get it working, get it some idea. And it's, it's pretty substantial piece of evidence, in my opinion, even not perfected, that this free momentum theory isn't going to work. It doesn't really happen in the real universe. That yes, there is something wrong with those experiments that show the creation of free momentum. The idea that you hit a one mass into a two mass and end up with 2/3 of the velocity in the two mass, meaning you created more momentum. That's a silly idea, frankly, on its face. It should be recognized by everyone that, man, you need really good proof if you're going to make that kind of statement. And we really don't have any even moderately decent proof. So, forced to do the experiment myself because physics can't manage it. So in 300 years they've had lots of opportunities to create some experiments that show kinetic energy theory in action, and especially this derivation of the theory where they predict that you can create free momentum, perpetual motion in a momentum universe, free energy in a momentum universe. That was the argument from the very origin of the debate over momentum versus kinetic energy. Was that you can't have it both ways. That one theory, if you believe in momentum, kinetic energy is a free energy theory. And if you believe in kinetic energy, momentum is a free energy theory. They aren't compatible ideas. One of them, they're either both wrong, or one of them's right and one of them's wrong. No choices here, really. Theoretically, there was no choices. A rational discussion of theory should get people to the conclusion that it can't be true that you can make free momentum. So anyway, let's just do, I'll provide all the raw files. So it's only like 3 minutes of video. Well, 4 minutes. And then a little short video just showing some of the mechanics of the air track. So the experiment's done about 30 times in the video. And, I sampled a few of those times and they all came out the same way. Less than half the momentum is transferred. Pretty close to half, actually, because a small cart almost comes to a complete stop. So we should be able to see that here. So the air track is on, and here comes the... So don't go by the holes. There's little gray lines, okay, you might be able to see if you look at the raw video. Let's go over here and we'll enlarge this. So there's little gray lines on here, okay, you can barely see them, but they're there, okay, you can see them, and they're inches with little half-inch marks, so it's half-inch marks on the scale. And so you can basically see in this example that it's almost a perfect half-inch going in, okay, just about a perfect half-inch. Half-inch, 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 always kind of ends up a little tiny bit shorter little line. Little tiny bit short, little tiny bit short, little tiny bit short, little tiny bit short. Alright, then there's rubber bands wrapped around the pipe. So the rubber bands are the only part hitting. The PVC doesn't come in contact with the PVC. It only hits rubber band. Alright. So it's not a perfect spring. So I'm going to do it with different springs. I'm going to do it with a tape measure, all that crap eventually. But I just figure I already know. We already got the answer, frankly. So I might as well show the answer before perfecting the answer. Alright, so here's the collision. So we'll move this appropriately so you can see it. Alright, that should help. Alright, so here's the leaving. So we had a half-inch going in, and you can already see it's a 1/4 inch coming out, okay, less than. Alright, so it's like that's a little bit short of a 1/4. Still hasn't quite gotten to the half-inch mark, the inch mark. You can almost see the inch mark, it's almost showing. And yeah, well, that line isn't very good actually, so it'd be better to go to the next line. Okay, so there's the line. We're a 1/4 inch past. We didn't quite get to the half. You can barely see the ½ inch mark, so it's clearly just basically a 1/4 inch. So you went from a half to a 1/4, 50%. And it's pretty clear in this one. I mean, you know, it's almost like it's stopping right on the mark, so it's almost like this is a perfect example. Just because, you know, the markings are, you know, it's 1/4 inch right on the half again, 1/4 inch right on the hole. I mean, you can't get more exact almost. And clearly this other cart isn't moving much, so I don't, you know, if I go regular speed we might see it drifting a little bit. Yeah, it's barely moving the other way. Alright, so basically all the energy was converted, and you need a very elastic collision for that to happen, so it is elastic. Now, whether it's 100% elastic, okay, there can be an argument about how perfect this is as a spring, but it's pretty good. So the video just has this done over and over again. Alright, so I go one way and then I do the 2 mass into the 1 mass, and you can see the 1 mass leaves with a little more velocity, like 130, 1.3 the velocity, the smaller mass, and the original mass loses, okay, that amount of momentum, and therefore it's reduced to like half its original speed. No, so I didn't do any measurements on those because that's not really the experiment under contention. So, like I said, if you want to go watch the raw videos there, I'll leave links there to I have them in a MOV format on the website. That's the original format of the camera. And then YouTube, I have them as unlisted videos, and I'll post the unlisted videos so you can watch them in however YouTube converts them, which may or may not be good frame rates. But anyway, it's pretty good quality video anyway. So I just redo the experiment, different speeds, very slow, very fast, blah blah blah. It always comes out the same way, you know. So later in the video, much later, 3:20 I guess we go to. So now I'm just showing I have a spring mechanism at the other end, another elastic at the end of the pipe, and I'm just trying to see how much velocity it loses as you throw it into the spring and have it just bounce back. How much of the energy do you lose from the spring device? And I didn't do the calculation. It just seems pretty good. It's like at least an 80% kind of thing, something like that. So this is just me doing, you know, trying to, the cart spins a little bit, and so there's a nail on one end, and if it does, well, a screw technically, and if the rubber band doesn't hit the screw, it doesn't come back, so I have to push it back. So it wasn't until, like, that was a good run. That one I missed. Okay, so this one is the start of a good run. Now it's a good bounce back. So you can see the speed going in and the speed coming back is almost the same. So it's a pretty good, so you can see that speed is pretty good. Pretty good going in, pretty good coming back. So the track is working pretty good, not much friction. It's a pretty good test, I think. Like I said, I haven't had time to really go through it and see what those speeds are, but it's working pretty good. Alright, so I'll switch to the other video that just shows the air track in a little more detail and such. Alright, so this video is just really just showing what the mechanism is. So I'm going to use, I haven't done launching it, but this is what I was throwing the cart into, was this rubber band stretched across a piece of steel clamped to the leaf blower. You know, that just allows the little screw to either, you know, hit into rubber bands and bounce it back. So I was just showing how well it bounces back off of this, technically this spring. So, and then eventually I'll have a little piece of wire attached to the rubber band, pull it back with this clothespin, and then release it and see, you know, do some tests by releasing from the springed, you know, the launcher, and it's pretty much, you're just basically saying it's like a slingshot. So I'm basically using a slingshot to launch things, And we'll see what happens with those experiments when I get to those. And so here's the cart, so you can see, it's just PVC pipe that's a little bit bigger than the pipe that has the holes in it. Don't use the holes to measure anything because I didn't mark it. I just, I wanted to do this quick just to see if it would work. I didn't even know if it would work as an air track, so I wasn't going to waste a bunch of time being precise. I just drilled the holes about 1 centimeter apart from each other. Didn't really worry about laying it out or doing any of that crap. And obviously it does work, so if it works when you're not even trying, it would probably work better if I do another one someday, but I don't know if I need to, frankly. But we'll see. I don't have perfectly straight edges. I have to file the pieces of PVC down. I didn't do that. It's really close to being twice the size. I didn't weigh them, so I don't really have a scale, frankly. So I'm going to get one of those eventually, but it's very close to being, one card is 1/2 the size of the other card. It's at least within 5% of double the mass. They have exactly the same attachments, blah, blah, blah. Which, technically the two mass should have twice as many rubber bands and another piece of wire, but the amount of weight that is so minor that I don't think it's really an issue. But you can see the little screw is what hits the rubber bands and bounces it back again. And you can see that part works pretty good. So this is just showing the rubber band again goes over the edge. It doesn't go down into the track at all. It doesn't touch the track. It doesn't overlap the edge. It just hangs over it like here's the end of the pipe. It just hangs over. So when the rubber bands hit each other, they do their rubber band thing, and so there's nothing hitting anything solid. It's just rubber band against rubber band. And that's about it. So I did copy sort of the design of the triangular air track in sense of I put holes at this angle, figuring I don't really need them to keep it from touching the sides. I just need enough pressure because it's not a huge threat hitting the sides. So I try to focus all the air to pushing it up because gravity is the thing you're trying to defeat. Now the good news is my leaf blower has 2 settings, high and low, and I got it to work on the low setting, so I didn't even have to resort to the really obnoxiously loud and irritating leaf blower. So that was good. So it gives me some capacity to add more weight to the carts, but I don't think I really want to do that. And such. I don't know if there's much else here to see. So it's a really simple design. That's the thing that's great about it, right? It's really cheap and simple. I figure it's pretty, actually it ends up being pretty level. So I should say that in the raw videos, the first run of the examples I do, it's tilted a little bit up. And then this, it's for you, it's the opposite way, this way. Okay, so the carts are going uphill. All right, I guess I have to do it this way. So the carts are going uphill a little bit. And then I switch it, so it's tilted a little tiny bit down. So now the carts are going downhill. And it made no real difference in the calculations. It came out the same both ways, frankly. And it was only a little bit off, Getting it perfectly levels, well, you can see in the video the carts aren't traveling anywhere, so the level's pretty good. They're not traveling very fast anywhere, let's put it that way. What's something else I want to say about that? So I figure in the future, if I was to make the track, this one's about, I don't know, 6 feet long, maybe 5. If I was worried about it bowing or doing anything like that, I was figured I can put a steel rod inside the track that would probably force it to stay without bowing any. But I really didn't see any issue, so I don't think it's a problem. And such. You can see most of that, right? So I just was pushing them back and forth without the track on. just to show how much resistance there really is when the track's not on. They obviously don't go very far, and there's quite a bit of friction, and blah, 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 blah. And that's an attempt to close up on the holes, but that didn't work too well. So I will eventually better mark it and all of that kind of crap. Maybe try to run the tape measure across the top, that kind of stuff. But the bottom line is I think it's enough evidence to confirm that my doubts are not unreasonable, that I have good reason to doubt Professor Lewin's experiment, to doubt the concept of free momentum, and even this, whatever you want to call it. To me, it's a perfectly valid experiment, but it does demonstrate that the effect isn't happening. There is no transfer of 2/3 of the velocity. It doesn't happen. Because if it did happen, it would be free energy, frankly, and the universe doesn't work that way. And so I think this is at least evidence or good reason for people not to be quite as so arrogant in their proclamations of what the truth must be. There's good reason to doubt Professor Lewin's experiment is credible. I had good reason to doubt 2 years ago, and now I have even better reason to doubt. And for what it's worth, frankly. I mean, I'm sorry if you're unpersuaded by any volume of evidence or any volume of logic. I mean, it doesn't matter how many times I ask the question, how can it be possible to create free momentum in this universe without that being free energy? Why wouldn't everybody do it if it really happens? If kinetic energy theory is correct, and I merely have to step on a lever to create free kinetic energy, why isn't everyone doing it? I mean, those are real questions that you haven't touched, and all you've done is arrogantly proclaim that your physics is, above any critique. Bad on you, frankly. Critics. So maybe I'll go through some of the crappy comments, but I'll save that for a website video tomorrow, maybe, because they are just such crap, But anyway, so I say pretty good piece of evidence, and at minimum, proving the respectability of my skepticism. At minimum, it does that. All right. I'm not just cranking for the fun of it. I'm making an argument because their physics doesn't really make sense. And this piece of hands-on, I touched it, I did it experiment confirms my suspicion that their physics is crap. Yeah, it's enough way of saying the same thing, I think. All right, so video 1. So I want to cut. I was thinking there's lots of ways I can do this, right? I can cut just a bunch of carts of different lengths, so I can just make them each one a centimeter bigger and do the experiment, just see how big a difference it makes, what size it is. That might be the way I have to go, just because attaching things to a cylinder is a little tricky, because you have to make it so it doesn't matter if it spins upside down or not. So that's the semi-tricky part. I can put weight on the bottom to force it to stay bottom heavy. But I don't know if I want to do that. But it's a possibility. I can just do that. Where their carts pile stuff on the top, I can just pile stuff on the bottom. But anyway, we'll see what I'm just going to search for different ways of doing it. Like I'm thinking of making a coiled spring, a handmade one that's the same size as the pipe. So the spring will stick out over the end, and have those as the springs they hit, something like that. But, we'll see what happens. I mean, it's a long summer. I should be able to find time to do some different experiments. Weather permitting. I mean, it's actually raining when I'm doing, when I filmed this. It was actually drizzling, but whatever. It's a minor inconvenience. So till the next time and such. This has been a draftphysics.com video presentation. Yeah, I told you so. Okay, so yeah, I'll say it. Told you so.